Hello everyone. So today's Geek for Geeks problem of the day is kth smallest number in multiplication table. I have given three integers m and k. Consider a grid m cross n where matrix of ij is I into j. Okay, one based indexing. Task is to return kth smallest element in the matrix. So we'll see the test cases. M is given as 3, n is given as 3. So 3 cross 3 is the matrix, and we have to return fifth smallest element. So let's fill the array first. One, as in the question is stated, one based indexing 1, 2, 3, 1, 2, 3. So matrix of ij is I into j. So 1 into 1 is 1. This is 2, this is 3, this is 2, this is 4, this is 6, this is 3, this is 6, and this is 9. So if we take a different color, so fifth smallest element we have to find. So the first smallest element is 1. Second is 2, third is also 2, fourth is 3, fifth is 3. So we have to return 3, and indeed that is our correct answer. So in this particular test case number 2, if we generate the array for m is equal to 2, n is equal to 3, we get this particular array, and this 1 is the first smallest element, second is the second, this is the third, this is the fourth, this is the fifth, this is the sixth. So this is the sixth element, the sixth smallest element, and indeed that is our correct answer. So let's see if this problem is actually solvable or not using brute force. So for the brute force method, the brute force is very simple. We'll create an external array of size n cross m, which is 3 into 3, which is 9 here. So we'll create a 9 size array and we'll fill the array. So let's suppose this is the imaginary array. We don't create this array, we create only this array. But for the explanation purposes, let's suppose that this is the matrix that we get, 3 cross 3 matrix, and we are filling this particular array. So this will be 1, 2, 3. This will be 2, 4, 6, and this will be 3, 6, 9. So as you can see, the fifth, it's asking the fifth element. So this is the first, second, third, fourth, fifth. So this is the fifth element. But can we return 4? No, because this array is not sorted. So we have to first sort this array. So 1, 2, 2, 3, 3, 4, 6, 6, 9. So after sorting the array, we can directly return the k minus 1th element, which is 0, 1, 2, 3, 4, which is k minus 1 is 4. So we have to return element at index number 4, and that is 3 here. In this case, as you can see, it is 3. So we have to return 3, and 3 indeed is our correct answer. So let's see the code for the same. So we'll create an array of size n cross n, and for filling this array, I've taken an pointer index starting from 0. So for iterating through every element, and index is starting from 1 because it says that it's 1 based indexing. So from I is equal to 1 to from j is equal to 1, I'll just multiply I into j and fill that in array, and I'll do index plus plus. After that, we have to sort the array. Filling is done. We have to sort the array. We have sorted the array, and directly we can return array of k minus 1. So the time, let's see the time complexity and space complexity for the same. So the time complexity for this operation is n cross n, and for sorting the array is nm, because the size of the array is nm. So nm log nm. So this is the time complexity, and space is, as we are using n cross m external array, so it would be n cross m. So let's see what we can optimize from this brute force method in the better approach. So for the better approach, we are going to use binary search. So let's see how we can use binary search. So as you can see, every element in the matrix is less than 9 and in the range of 1 to 9. So how did we get 9? 3 into 3, which is m and n. So we get 9. How did we get 1? We get 1 because it's a one indexed array. So 1 cross 1 is 1. So 1 into 1 is 1. So the range is from 1 to 9. So instead of creating an array, we can directly use this as a range. So the low value will be 1 and the high value will be 9. So let's see if this is low, this is high, and the standard binary search, this will be, let's mark the index first, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. Low will be this, high will be this, and mid will be 8 plus 0 by 2, which is 4. Mid will be here. So for mid, we'll calculate what is the position of this particular index in the complete array. So this will be the fifth smallest element, as you can see, 1, 2, 3, 4, 5. So this is the fifth smallest element. So if it's fifth smallest element, we'll make high as mid. We'll make high as mid. So let's see what will happen now. 4 plus 0 by 2 is mid will come at 2. So for this is the third smallest element. 1, 2, 3. So we don't want third, we want the fifth. So we'll increase low and make it mid plus 1. Low will come to mid plus 1. So 4 plus 3 by 2 is 3. So mid will be here. So this particular index, this is the fourth smallest element, but we need the fifth smallest element. So again, we have to increase the low value. So low will come here. So whenever low and high meet, we directly we break the loop and we directly return low. Low or high, you can return either of them because both of them are same. So in this particular manner, binary search is very helpful because instead of creating an array which will take n into m memory space, we are using big of one memory space, as well as we are decreasing the time complexity for the for finding the m value. So because we if we are finding the fifth smallest element, why would we search below after 5? Because this is the sixth, seventh, and eighth element. Do we need that? No, we don't need. So we can directly eliminate this part, this sub part of the problem. So we are solving a problem and we are dividing it. So that is why the complexity will become log nm, which is much better than n cross m or any other uh, value of this. So, and if we are finding the sixth element, let's suppose this is low, this is mid, and this is high. So if we are finding high as seventh element, and this will be the fifth element, but we need seven, so we'll directly eliminate this complete sub problem. We'll move left to mid plus one. We'll move left to left mid plus one, and we'll directly search for this particular sub array, sub problem. So 8 plus 5, which is 13. 13 by 2 is 6. So mid will come here. So this is the 1, 2, 3, 4, 5, 6, 7. So 7. So we'll directly make high is equal to mid. High will come here. So again mid will come here because 6 plus 5 is 11. 11 by 2 is 5. So this is the 1, 2, 3, 4, 5, 6. Sixth element, but we need 7. So we have to make low as mid plus 1. So low will come here. So whenever low and high meet, we directly return the value of low. This is how we optimize this from brute force. So let's see that algorithm. We'll use range starting from 1 to nm, as you have seen, for binary search, taking one half of the range and eliminating the other. So for the mid value, we'll calculate how many numbers are smaller than this so that we get to know what is the position of this particular m, whether it's the fifth element, fifth smallest element, or the fourth smallest element. We get to know for that. So we are using nm for calculating the position of that particular index, and log nm for this particular binary search. So let's see how we can optimize this time complexity in the optimal approach. Space complexity is big of 1, so we cannot further optimize the space complexity, but we can still further optimize time complexity. So let's see the optimal approach. So this approach is also very similar to the better solution, but in this, instead of going through every element, we use here the binary search even for calculating the count. If you know upper bound of a binary search, if you don't know, I'll highly suggest you to go ahead and study about binary search, upper bound and lower bound. So for this particular question, we use upper bound. I'll explain you why you use upper bound. So instead of checking every index in the matrix, we could use binary search to find the upper bound of a number. So this part remains the same as the better approach. We'll only go through this and why we are using binary search instead of normal n cross n. So this is high, this is low, and this is mid, as we have seen already in the previous exam, previous approach. So for 3, can we find the upper bound? Upper bound means a number which is just greater than the number we are finding. So let's suppose the target is 3. Target is 3. So any number which is greater than 3 will be the upper bound. So for the first row, we'll see what is the upper bound. Upper bound is this element, which doesn't exist. So it will be, this is 0, 1, 2, 3. This is 0, 1, 2, 3. So upper bound will be this. So 3 will be the upper bound. Index number 3 will be the upper bound. So we'll return 3. For this, it will be 3. For the second row, it will be this because it is greater than 3. So it is 1. So we'll return 1. 1, what is the meaning of 1? 1 is number of elements smaller than the target element. So for the first row, it returned us 3, which is the correct because 1, 2, 3 elements are greater than, less than or equal to the target element. In the second row, it is returning 1, which is also correct. So in the third row, you can see the upper bound is 6 and it will return the index 1. So it will be 5. So like this, we are able to solve the problem of n cross m into n cross log m, as we are using the binary search to do the same. We'll take one more. We'll take one more m value. Suppose we are taking m value as 6. So for this, let's see what will be the count for 6. So for 6, again the upper bound will be pointing to index number 3. So it will return 3 for this. For the second as well, it will point to 3 because 6 is not greater than 6. So it will return 3 here as well. Here in the third row, it will return index number 2. So it will return index number 2. So 3 plus 3 plus 2, which is 8. And it is the 8th largest element. 1, 2, 3, 4, 5, 6, 7, 8. It is indeed the 8th largest element. So this is how we come across this particular question. It is a very good question when you talk about binary search, because this kind of questions where you have to find the first you have to understand that this is a binary search, then we have to apply multiple binary search approaches. So the time complexity, let's see the time complexity for this. So n, so let's go by this. This is log nm because we are going through 1 to n cross m, and this particular piece of code will give you, this is row wise, so number of rows are n, so it's n cross, this is log m. So n log m log nm, and the space complexity is 1. So instead of n cross m, we are getting n log m, which is much better than n square. So this is the three approaches, and hope you understand all the three approaches. Thank you for watching. Bye.